Now that we've learned about aldol reactions and aldol condensations, we're going to take a look at intramolecular aldol reactions. And what happens here is that the piece that's acting as the enolate and the piece that's acting as the carbonyl are on the same carbon chain, and therefore what you end up with is a ring that you didn't have before. And in order to talk about this, I use this concept of outside enolates and inside enolates. So a couple things to keep in mind. Remember that 5 and 6 membered rings are more stable than smaller rings or larger rings. And so we're going to stick to making 5 and 6 membered rings. And so that's what this table shows you. Yes, you can make smaller ones or bigger ones, but we're not going to deal with that. We're also ultimately going to be able to apply this to Dieckmann condensations, which are intramolecular Claisen condensations. But keep in mind that aldehydes and esters can only make inside enolates because the only thing on the outside is either a hydrogen or an alkoxy group, and those are not going to make enolates. So the way this table is set up, I have the relative position of the two carbonyls. So you have a 1,4, 1,5, 1,6, 1,7 carbonyl. Whether the product that forms a 5 or 6 membered ring results from an outside enolate or an inside enolate, the ring size that you end up with as a result, and then I go through an example of each. And for consistency, I did a couple of things. One of them is that these are all diketones. The other is that throughout I made the one that reacts as the carbonyl the number 2 carbon, just to make people's lives easier. And I use this numbering system basically just to keep track of the carbons. It makes it easier to figure out what went where, and it's also easier to see the new bond that's formed. So here are the start of 2 of the reactions. They happen to be the first 2. So here we have a 1, 2, 3, 4. So the 1,4-dicarbonyl is not, we're not trying to name this thing, we're just trying to give the relative position of the 2 carbonyls. So in this table, we only deal with symmetrical ketones. So there's only one enolate that you can effectively make. Same thing would be true if you had an aldehyde with no substituents on the inside part, because there would only be one enolate you could make, or if you had, like a ketone and an aldehyde. But again, we're sticking with diketones here because they're simpler. And so the first thing that's going to happen is that we're going to remove this acidic hydrogen, and I didn't show arrows for that, but you just remove that. And then I chose to keep the lone pair on the carbon and not show the resonance contributor. And then here's the numbering system, 1, 2, 3, 4, 5, 6. And so carbon 6, the outside enolate, attacks the carbonyl carbon, and we get this compound where the new bond is between carbon 2 and carbon 6. The new bond is going to be between 2 carbons that don't have consecutive numbers because you've stuck different parts of the chain together. And then this can go on and react. So this would be the result of an outside enolate. This compound, actually either one of them, this compound can either make an outside enolate or an inside enolate. But if it makes an outside enolate, the size ring that we're going to end up with is a 1, 2, 3, 4, 5, 6, 7. And that's not particularly likely. So we're going to go with the inside enolate, which would give us a 1, 2, 3, 4, 5 membered ring from this 1, 2, 3, 4, 5, 6 dicarbonyl. So we remove this proton in order to get to the product. Do we remove other protons? Probably, but we're going to write a mechanism for the one that gives us the product that we want. And then this inside enolate, so-called because the enolate is inside the two carbonyls as opposed to on the outside of the two carbonyls, attacks the carbonyl carbon, and again, we get a 5-membered ring, and you can see the numbering. So with both of these compounds, there is more than one enolate that you can make. This one can make this enolate or this enolate. But if you were to make this enolate here, you'd have a 1, 2, 3-membered ring. Not very likely. So we go with the 1, 2, 3, 4, 5-membered ring. Same thing here. This could either make the 7-membered ring that I showed you or the 5-membered ring that we see. Notice that our options are always going to be 2 apart. So this technically has the option of a 3 or a 5-membered ring, and we see the 5-membered ring. This has an option of either the 5 or the 7, and we see more of the 5 than we do of the 7. So you're never going to have a choice between a 5 and a 6 because those are consecutive numbers. So just looking at the examples, I showed you the 1, 4 and the 1, 5, the 1, 4 and the 1, 6. Dicarbonyls below, so those have examples that are below, the 1, 4 and the 1, 6, because I wanted to show you one outside and one inside. So if you have a 1, 5 dicarbonyl compound, so 1, 2, 3, 4, 5 carbons apart, again, we technically have 2 choices. We could make the enolate at carbon 5 and have that attack carbon 2, which would give us a 1, 2, 3, 4-membered ring. No. Or we can make the outside enolate, and then we'll end up with a 1, 2, 3, 4, 5, 6-membered ring, which is what we see. And in all of these cases, I draw the structure of the aldol reaction and then the condensation, what you would get if you added heat and or you had this double bond was, say, in conjugation to other double bonds or especially an aromatic ring. So again, here the choice is 4-membered or 6-membered. Then this is the one that I did down below. And then the last one we'll look at is the 1, 7 dicarbonyl, because anything with the carbonyls closer together or further apart is going to give us ring sizes that are either smaller than 5-membered or larger than 7-membered. And so again, we have the potential for 2 enolates. We can either make the inside enolate here, which would give us a 1, 2, 3, 4, 5, 6-membered ring, which is the observed major product. We could make the outside enolate, but that's going to give us a 1, 2, 3, 4, 5, 6, 7, 8-membered ring. Not very likely. Small rings and large rings each have issues with respect to ring strain. The small rings have angle strain and torsional strain. The larger rings also have some strain because they're not that ideal 6-membered ring. The other factor with making large rings is as the 2 ends that have to react get further and further apart, it becomes likelier that each end will react with a different molecule rather than with the other part of itself. So if you want to make those large macrocyclic rings, what you need to do is do the reaction under very dilute conditions that make it far, far likelier for the compound to find itself than another one. But that kind of digressed from this. But the point is that we tend to make these 5-membered rings and 6-membered rings. And, this just kind of summarizes it. You don't see this whole inside-outside notation in textbooks. At least I've never seen it in a textbook. I actually invented it just as a way to talk about the reaction, because when you're trying to figure out the reaction products, it's much easier if you can look at this and talk about the concept of an outside versus an inside enolate. It's just language to make things hopefully easier. So one additional thing I wanted to look at was the relative position of the 2 carbonyls versus the ring size. And if you look at the outside enolates, you can see a mathematical relationship. So when I'm actually teaching live, what I do is I ask the class if they can see what the relationship is here, but I'm just going to tell you. So for the outside enolates, if you add the 2 relative carbonyl positions, you get the ring size. And again, that's not something I'm going to test you on, but it's something that you can have in the back of your head as a way of checking your product, or maybe even doing a multiple choice question quickly. With the inside enolates, you subtract. So 6 minus 1 is 5, 7 minus 1 is 6. And again, this is just a handy way of being able to talk about these reactions and hopefully make them a little bit easier to understand, because I think reactions that make rings and open rings are among the harder ones to understand mechanistically. And again, just as a reminder, aldehydes are going to do this as well as ketones, but aldehydes can only make inside enolates because there's a hydrogen on the outside. And we'll also be able to apply this to Dieckmann condensations, which are just intramolecular Claisens with a different name. But again, esters can only make inside enolates, not outside enolates. So for both dialdehydes and diesters, using this chart, we would only have these two possibilities because those are the two inside enolate possibilities. As part of the first set of writing the reaction product examples that I do, some of the examples will be intramolecular reactions.